For centuries, the success of classical physics created a powerful psychological effect on humanity. It did more than explain nature, it shaped how people believed reality itself was structured. By the late 18th and 19th centuries, physics appeared not as a work in progress, but as a completed cathedral of knowledge. The laws describing motion, force, energy, heat, and light seemed universal and final. They worked with astonishing precision across an enormous range of everyday phenomena, from the swing of a pendulum to the orbit of planets. This success produced a deep conviction that the universe was fundamentally understandable in a simple, mechanical way. At the heart of this confidence was the idea that nature was continuous, deterministic, and objective. Every physical quantity was assumed to have a definite value at all times, whether or not it was being measured. Position, velocity, energy, and time flowed smoothly without jumps or gaps. Change occurred gradually, not abruptly. Causes led to effects in a perfectly predictable chain. If something happened, it happened because it had to, not because it might. This view of reality aligned beautifully with human intuition and everyday experience, reinforcing the belief that classical physics was not merely a useful model, but a literal description of how the universe truly worked. The philosophical implications of this worldview were enormous. If the universe operated like a giant clockwork mechanism, then in principle, everything was knowable. A sufficiently intelligent observer, given complete information about the present, could calculate the entire future and reconstruct the entire past. This idea was not a fringe interpretation, it was openly embraced by leading thinkers. The universe was imagined as a vast machine, its gears turning according to fixed laws that left no room for ambiguity. Chance, uncertainty, and randomness were seen as signs of human ignorance, not features of nature itself. This sense of completeness was reinforced by the extraordinary achievements of classical physics. The laws of motion described by Isaac Newton unified terrestrial and celestial phenomena under a single mathematical framework. The same equations explained falling apples and orbiting moons. Later developments in thermodynamics explained heat, work, and energy with remarkable generality. Electromagnetism united electricity, magnetism, and light into a coherent theory that predicted new phenomena before they were observed. Each success strengthened the belief that physics was steadily approaching a final, all-encompassing explanation of reality. By the late 19th century, many physicists believed that the fundamental laws were already known. What remained, they thought, was merely the refinement of measurements and the application of existing theories to increasingly complex systems. The major intellectual battles appeared to be over. Physics had become, in the minds of some, a mature science with no revolutionary surprises left to offer. Students were warned that the future of physics lay not in discovering new principles, but in improving precision and extending calculations to the 5th or 6th decimal place. This confidence was not arrogance without foundation. Classical physics worked spectacularly well in the macroscopic world. Engineering, astronomy, navigation, and industry all relied on its principles, and they worked. Bridges stood, machines functioned, and predictions matched observations with stunning accuracy. Every practical success reinforced the idea that the theoretical foundation was solid and complete. It was difficult to imagine that such a powerful framework could fail in any fundamental way. Yet hidden beneath this success was a subtle but critical assumption that the same laws governing large, visible objects must also govern the smallest constituents of matter and energy. Classical physics made no distinction between scales. It assumed that if you could zoom in far enough, you would simply find smaller versions of the same mechanical processes. Tiny particles would behave like miniature billiard balls. Waves would remain waves at all scales. Energy would always flow smoothly, never in sudden jumps. This assumption seemed so reasonable that it was rarely questioned. The illusion of completeness was strengthened by the mathematical elegance of classical theory. The equations were beautiful, symmetric, and logically coherent. They formed a closed system in which every variable had a clear meaning and every effect had a precise cause. There were no contradictions within the theory itself. Any mismatch between prediction and experiment was usually attributed to experimental error or incomplete understanding of initial conditions. The idea that the theory itself could be fundamentally wrong was almost unthinkable. This mindset shaped the culture of physics. Young scientists were trained to believe that the basic structure of reality had already been uncovered. Creativity was directed toward solving complex problems within the existing framework, not toward questioning the framework itself. The deepest questions appeared settled. Nature, it seemed, had already revealed her core secrets, and all that remained was careful bookkeeping. However, this sense of closure contained a dangerous vulnerability. A theory that appears complete becomes resistant to criticism. When anomalies arise, they are treated as inconveniences rather than warnings. At first, small discrepancies were dismissed as technical issues that would eventually be resolved without altering the underlying principles. The belief in completeness acted as a filter, shaping how evidence was interpreted and which questions were considered legitimate. As experiments became more refined, physicists began probing domains that classical physics had never truly been tested in before. High temperatures, very small scales, and interactions involving light and matter at the atomic level revealed behaviors that did not align with classical expectations. At first, these inconsistencies were subtle. They did not immediately threaten the grand structure of the theory. But they accumulated, slowly and persistently, like cracks forming in a seemingly solid foundation. What made the situation especially unsettling was that these failures did not arise from speculative philosophy, but from carefully controlled experiments. The laboratory, not abstract reasoning, began to undermine the illusion of completeness. Nature itself was contradicting the equations that were supposed to describe it perfectly. The universe was not merely deviating slightly from predictions. In some cases, it was behaving in ways that classical physics declared impossible. The growing tension exposed a critical flaw in the earlier confidence: success in one domain does not guarantee universal validity. Classical physics had been extrapolated far beyond the range in which it had originally been tested. Its triumphs in the everyday world had encouraged scientists to assume that its principles were absolute. This assumption, though understandable, was never experimentally proven. It was an act of faith disguised as reason. As doubts began to surface, the psychological impact on the scientific community was profound. If classical physics was incomplete, then the entire philosophical picture of a deterministic, mechanical universe was in question. The implications extended beyond physics into philosophy, metaphysics, and even human self-understanding. If nature was not fully predictable, what did that mean for causality, free will, and the limits of knowledge? The illusion of completeness did not shatter all at once. It resisted collapse because classical physics continued to work extremely well where it always had. The same equations that failed spectacularly at microscopic scales remained perfectly accurate for planets, projectiles, and machines. This duality created confusion rather than clarity. How could a theory be both extraordinarily successful and fundamentally wrong? The answer, though not yet fully realized at the time, was that classical physics was not wrong in the sense of being useless. It was wrong in the sense of being incomplete. It described a particular layer of reality, not reality in its entirety. The mistake was not in the equations themselves, but in the assumption that those equations represented the final word on nature. The first keynote, the illusion of completeness, is therefore not merely a historical footnote. It is a lesson about how scientific confidence can harden into dogma. It shows how deeply human intuition and philosophical comfort can influence scientific belief. Classical physics failed not because it lacked brilliance, but because its success blinded its practitioners to its limitations. This illusion had to break before deeper truths could emerge. Only when physicists accepted that their most trusted framework might be fundamentally incomplete could a new understanding of nature take shape. The collapse of certainty was not a setback, it was a necessary step toward a more accurate, though far stranger, picture of reality. As the illusion of completeness began to weaken, a deeper problem revealed itself. Classical physics had quietly merged mathematical success with philosophical certainty. Equations that worked extraordinarily well were assumed to describe reality itself, not just approximate it. This subtle shift went largely unnoticed because the predictions were so accurate in familiar situations. When a theory predicts eclipses centuries in advance or allows engineers to build machines that function flawlessly, it feels natural to trust it completely. But predictive power is not the same as ontological truth, and this distinction would become painfully important. Classical physics treated measurement as a passive act. Observing a system was assumed not to disturb it in any meaningful way. The world existed independently of observers, with all properties fully defined at every moment. This assumption was so deeply ingrained that it was rarely stated explicitly. It was simply taken as obvious. The universe was out there, running on its own, and science merely uncovered what was already happening. This belief reinforced the idea that physics was revealing ultimate reality rather than constructing models that worked within certain limits. Another source of the illusion was the smoothness of classical descriptions. Motion was continuous, energy changed gradually, forces acted through space in a well-defined manner. There were no sudden jumps, no discontinuities, no gaps where the theory lost its grip. This continuity matched everyday experience perfectly. You never see a ball teleport from one place to another or a pot of water suddenly skip intermediate temperatures. Because human perception evolved in this macroscopic world, classical physics felt intuitively correct. It confirmed what people already believed about how reality should behave. The danger of intuition, however, is that it does not scale. Human senses are adapted to a narrow range of sizes, speeds, and energies. Classical physics silently assumed that intuition remained valid far beyond that range. It assumed that nature at extremely small scales behaved like a refined version of nature at human scales. This assumption was never tested directly until technology made such tests possible. When experiments finally reached into the atomic and subatomic domains, intuition failed catastrophically. The belief in completeness also shaped how anomalies were treated. When experimental results did not align with classical predictions, the immediate response was not to question the theory, but to question the experiment. Instruments were recalibrated, procedures refined, and errors hunted down. Often the skepticism was justified. Experiments are difficult and mistakes are common. But over time, a pattern emerged. Different laboratories, using different methods, were observing the same discrepancies. These were not isolated accidents. They were consistent signals that something fundamental was wrong. Still, the resistance to abandoning classical completeness was immense. The theory was too successful, too beautiful, too foundational to discard lightly. Entire scientific careers were built on it. Textbooks, institutions, and industries depended on it. Letting go of the idea that it was complete felt like stepping into intellectual chaos. If the most trusted framework in science could fail, what could be trusted at all? This psychological resistance delayed recognition of the crisis. Instead of seeing anomalies as signs of a deeper breakdown, many physicists treated them as puzzles that would eventually be solved within the existing framework. Small fixes were proposed, auxiliary assumptions added, and mathematical tricks employed to force agreement with experiment. These efforts sometimes worked temporarily, but they never addressed the underlying contradictions. The theory was being patched, not healed. The illusion of completeness was also sustained by the compartmentalization of problems. Failures in one area were treated as isolated issues rather than symptoms of a broader breakdown. Radiation problems belonged to thermodynamics. Atomic stability issues belonged to chemistry. Light-matter interactions belonged to optics. Classical physics seemed intact as long as no one tried to view these failures as connected. It took a conceptual shift to recognize that all these anomalies pointed toward a single conclusion: the classical picture of reality was incomplete at a fundamental level. As more cracks appeared, a new realization slowly emerged. The laws of physics might not be universal in the way people had assumed. They might depend on scale, context, and conditions. A theory could be extraordinarily accurate in one domain and completely wrong in another. This idea was deeply unsettling because it challenged the notion of absolute laws governing everything uniformly. It suggested that nature might be layered, with different rules applying at different levels. This realization transformed the meaning of scientific knowledge itself. Physics was no longer seen as a steady march toward a single, final truth. Instead, it became a process of building models that work within specific limits. The goal shifted from discovering ultimate reality to understanding which descriptions apply where and why. The illusion of completeness had to be abandoned for science to move forward. What made this transition especially difficult was that classical physics did not fail gradually. In some cases, it failed completely and spectacularly. Its predictions were not just slightly off, they were infinitely wrong. Such failures could not be ignored or explained away. They demanded a radical rethinking of fundamental assumptions. Continuity, determinism, and objectivity, all pillars of the classical worldview, were suddenly open to question. The collapse of the illusion also exposed the limits of human-centered reasoning. Nature was not obligated to conform to what seemed reasonable or intuitive. Reality did not care about philosophical comfort. The universe behaved according to rules that could be deeply counterintuitive, even shocking. Accepting this required humility, an acknowledgement that human intuition, shaped by everyday experience, was not a reliable guide to the deepest layers of nature. In retrospect, the illusion of completeness appears almost inevitable. When a theory works as well as classical physics did for as long as it did, confidence is unavoidable. But history shows that scientific progress often requires the courage to question even the most successful ideas. The downfall of classical completeness was not a failure of intelligence, but a consequence of success taken too far. This lesson extends beyond physics. It is a warning about the dangers of mistaking usefulness for truth and precision for finality. Classical physics taught humanity how powerful scientific models could be. Its failure taught humanity how limited they ultimately are. Together, these insights reshaped the philosophy of science itself. The breaking of the illusion did not destroy classical physics. It placed it in proper context. It remained an essential tool for understanding the macroscopic world, but it could no longer claim to be the final description of reality. By letting go of the belief in completeness, physicists opened the door to deeper theories that could explain what classical physics could not. The end of this illusion marked a turning point. It was the moment when certainty gave way to curiosity, when confidence gave way to questioning. It prepared the ground for a revolution that would redefine reality, knowledge, and the limits of human understanding. Without the collapse of this first keynote, the illusion of completeness, nothing that followed would have been possible. For a long time, classical physics survived not because it was perfect, but because experiments were limited. Nature had many secrets, but humanity lacked the tools to interrogate her deeply. As instruments improved in precision and sensitivity during the late 19th century, experiments began to venture into regimes where classical laws had never truly been tested. What scientists found there was not refinement or confirmation, but rebellion. Reality itself began to violate the rules that physics had confidently declared universal. One of the earliest and most disturbing signs came from experiments involving light. Classical physics treated light as a wave propagating through a medium, much like sound travels through air. This invisible medium was called the ether, and its existence was considered obvious. If light was a wave, it needed something to wave in. The ether was assumed to fill all of space, absolute and stationary, providing a universal reference frame against which motion could be measured. An experiment was devised to detect Earth's motion through this ether by measuring changes in the speed of light in different directions. According to classical reasoning, light traveling with or against Earth's motion should move at different speeds, just as sound behaves differently depending on wind direction. The experimental setup was elegant, sensitive, and theoretically airtight. Yet, when the measurements were made, the expected difference did not appear. Light moved at the same speed in all directions. No trace of the ether could be found. This result was not merely surprising, it was devastating. The experiment had been designed specifically to confirm a cornerstone of classical wave theory. Instead, it contradicted it completely. Scientists repeated the measurements, refined the apparatus, and checked for errors. The result remained unchanged. The universe refused to cooperate. The ether, so essential to classical explanations of light, appeared not to exist at all. Around the same time, other experiments involving light produced equally troubling results. When light was shone onto certain metal surfaces, electrons were ejected. Classical physics predicted that increasing the intensity of light should increase the energy of the ejected electrons, regardless of the color of the light. Experiments showed something radically different. Below a certain frequency, no electrons were ejected at all, no matter how intense the light was. Above that frequency, electrons were ejected instantly, even at low intensity. This behavior made no sense within classical wave theory. Energy in a wave should be spread continuously, not delivered in discrete bursts. Yet the experiment clearly showed that light transferred energy in indivisible packets. Increasing brightness increased the number of electrons ejected, not their individual energies. Nature was not merely bending the rules, it was operating according to a completely different logic. Heat and radiation experiments delivered another blow. When scientists studied how hot objects emitted radiation, classical theory predicted a smooth increase in emitted energy as frequency increased. According to the equations, short wavelength radiation should dominate, leading to infinite energy output. This was not a subtle mismatch, it was a catastrophic failure. Real objects emitted finite energy, with a clear peak and decline. No amount of mathematical adjustment could fix the divergence. The theory predicted something that did not and could not exist. Atomic experiments were even more unforgiving. Classical physics imagined atoms as tiny mechanical systems, with electrons orbiting nuclei like planets around a star. According to electromagnetic theory, accelerating charges must emit radiation. Orbiting electrons were constantly accelerating, which meant they should lose energy and spiral inward. Calculations showed that atoms should collapse in a tiny fraction of a second. Yet matter was stable. Every solid object, every living organism, every star in the sky was evidence that atoms did not behave as classical physics demanded. Spectroscopy revealed another contradiction. When atoms emitted light, they did not produce a continuous spectrum, as classical theory predicted. Instead, they emitted light at precise, discrete wavelengths, forming sharp lines with exact regularity. Each element had its own unique pattern, like a fingerprint. Classical physics had no mechanism to explain why atoms would allow only certain energies and forbid all others. The discreteness was undeniable, repeatable, and universal. Even experiments designed to confirm classical ideas began to undermine them. Attempts to measure the behavior of electrons showed that they did not follow well-defined paths. Instead of tracing smooth trajectories, they appeared to exhibit both wave-like spreading and particle-like impacts. Devices built to detect particles produced interference patterns characteristic of waves. Instruments designed to observe waves registered localized, particle-like hits. No classical concept could reconcile these results. What made these experimental failures especially alarming was their consistency. Different laboratories, different countries, different experimental methods all pointed to the same conclusion. The contradictions were not accidents. They were features of nature. Classical physics was not being challenged at its margins, it was being contradicted at its core. At first, physicists attempted to save the classical framework by modifying assumptions. Ad hoc hypotheses were introduced to explain individual anomalies. The ether was given strange properties. Energy loss mechanisms were selectively ignored. Mathematical tricks were used to cancel infinities. These efforts created increasingly artificial theories that worked only by coincidence and lacked explanatory power. Each patch fixed one problem while creating another. As the experimental evidence accumulated, it became impossible to ignore the pattern. The failures were not isolated puzzles, they were interconnected symptoms of a deeper crisis. Light, heat, matter, and motion were all behaving in ways that violated the same classical assumptions: continuity, determinism, and independence from observation. The universe was sending a clear message that these assumptions did not apply at small scales. One of the most unsettling aspects of these experiments was their indifference to human expectations. Classical physics was built on logic, mathematics, and intuition refined through everyday experience. Experiments showed that nature did not care about any of these. Reality followed rules that could be mathematically precise yet conceptually alien. The experimental results were not ambiguous or subjective. They were precise, reproducible, and unforgiving. This created a profound psychological shock within the scientific community. Physics had always advanced by aligning theory with experiment, but now experiments were demanding a complete rethinking of theory itself. The trusted language of forces, trajectories, and continuous motion was no longer sufficient. The universe was not just more complex than expected, it was fundamentally different from what classical physics had imagined. Importantly, these experimental failures did not suggest that classical physics was useless. On the contrary, it continued to work perfectly in its traditional domain. But experiments were revealing that nature was layered. The rules governing everyday objects were not the same rules governing atoms and light. Classical physics was a special case, not the foundation. The second keynote, the experiments that refused to obey the rules, represents the moment when reality asserted its authority over theory. No philosophical argument could override experimental fact. No mathematical elegance could compensate for empirical failure. Nature was not obligated to follow human ideas, no matter how successful those ideas had once been. These experiments did more than expose errors. They forced physics to confront a humbling truth. Understanding the universe required abandoning deeply held assumptions. Observation was not passive, energy was not continuous. Determinism was not absolute. The behavior of nature, at its most fundamental level, could not be captured by classical intuition. This confrontation marked a turning point in the history of science. When experiments refused to obey the rules, physics was compelled to change the rules themselves. The crisis was not resolved by minor corrections, but by a radical transformation in how reality was described. The universe had spoken through experiment, and classical physics had no choice but to listen. As the weight of experimental contradiction grew heavier, the deeper meaning of these results began to sink in. The experiments were not merely showing that classical equations failed to match observations. They were revealing that the very questions classical physics asked were sometimes meaningless in the regimes being explored. Concepts that had once seemed fundamental, such as exact position, precise trajectory, and continuous energy flow, were losing their physical relevance. Nature was not just disobeying the rules, it was exposing the limits of the language in which those rules were written. One of the most unsettling realizations was that experimental outcomes depended on how measurements were performed. In classical physics, measurement was assumed to reveal pre-existing properties. An object had a position, a speed, and an energy whether or not anyone looked. Experiments at small scales suggested otherwise. The act of measurement itself appeared to influence what was observed. This was not due to clumsy instruments or experimental disturbance in the ordinary sense. It was intrinsic. Certain properties could not be simultaneously defined with arbitrary precision, no matter how ideal the apparatus. This realization struck at the heart of objectivity. Classical physics assumed that the universe existed independently of observers in a fully defined state. Experiments were now suggesting that some aspects of reality only took definite form when measured. This was not philosophical speculation. It was an unavoidable conclusion drawn from repeated, carefully controlled experiments. The universe seemed less like a fixed machine and more like a system of possibilities that crystallized under observation. Another disturbing feature was the appearance of irreducible randomness. Classical randomness was always temporary, a reflection of ignorance. If you did not know all the details, outcomes appeared random, but with complete information, certainty was restored. Experiments at atomic scales showed randomness that could not be eliminated, even in principle. Identical preparations produced different outcomes, not because something was hidden, but because nature itself was probabilistic. The same experiment, performed under the same conditions, did not yield the same result every time. This forced a dramatic reinterpretation of causality. In the classical worldview, causes uniquely determined effects. Given the same cause, the same effect must follow. The new experimental evidence suggested a different relationship causes constrained probabilities rather than dictating outcomes. Physics was no longer about predicting exactly what would happen, but about predicting the likelihood of different possibilities. This was not a failure of predictive power, but a change in its meaning. Attempts to rescue classical causality grew increasingly strained. Some physicists hoped that hidden mechanisms might restore determinism if only they could be uncovered. But experiments repeatedly closed these loopholes. Tests designed to reveal underlying deterministic structures instead confirmed that no such structures could reproduce the observed results without abandoning other well-established principles. The universe appeared stubbornly resistant to classical explanation. Equally troubling was the way particles and waves blurred into one another under experimental scrutiny. Classical physics treated them as fundamentally distinct categories. Experiments showed that this distinction broke down completely at small scales. Entities exhibited wave-like interference when not observed and particle-like localization when detected. This behavior was not optional or context-dependent in a classical sense, it was unavoidable. The same entity could not be cleanly classified as one thing or the other. This dual behavior was not a temporary confusion awaiting clarification. It was a stable, repeatable feature of nature. Every attempt to force it into a classical category failed. The experiments were not incomplete. They were complete enough to rule out classical interpretations entirely. Nature was revealing that its fundamental building blocks did not conform to human-made classifications. The accumulation of these results created a profound conceptual crisis. Classical physics had been built on a small set of assumptions that seemed self-evident: continuity, determinism, separability, and observer independence. Experiments were systematically dismantling each of these. Energy was quantized. Outcomes were probabilistic. Systems could not always be treated as independent. Observation mattered. These were not minor revisions, they were foundational shifts. What made the situation even more difficult was that there was no single experiment that caused the collapse. The crisis emerged from the convergence of many independent lines of evidence. Each experiment alone might have been rationalized or ignored. Together, they formed an overwhelming case. Light, matter, heat, and motion were all telling the same story in different languages. Classical physics was not just incomplete, it was conceptually incompatible with the behavior of the microscopic world. The response within the scientific community was mixed. Some embraced the need for radical change, while others resisted fiercely. The discomfort was understandable. Accepting the experimental verdict meant accepting that deeply cherished ideas about reality were wrong. It meant acknowledging that intuition, refined over millennia, was unreliable at fundamental scales. It meant admitting that the universe was stranger than anyone had imagined. Gradually, a new attitude toward theory began to emerge. Instead of demanding that nature conform to preconceived ideas, physicists began allowing experimental facts to guide the construction of new concepts. This was a reversal of priorities. Theories would no longer dictate what experiments should find, experiments would dictate what theories must become. Mathematics would still be essential, but it would serve empirical reality rather than philosophical preference. This shift transformed the role of experimentation itself. Experiments were no longer merely tests of theory, they became sources of conceptual insight. They revealed not just numerical discrepancies but new principles. The failure of classical predictions was not a dead end, it was a map pointing toward deeper structure. Each contradiction hinted at a rule that classical physics had overlooked. The second keynote therefore represents more than a catalog of failed predictions. It marks the moment when reality asserted its independence from human expectations. The universe was not obligated to be simple, intuitive, or comforting. It operated according to its own logic, and that logic had to be learned, not assumed. In retrospect, the refusal of experiments to obey classical rules appears inevitable. Classical physics had been extrapolated far beyond the domain where it was born. Its success in describing the visible world had encouraged unjustified confidence in its universality. Experiments at small scales exposed the cost of that confidence. They revealed that nature was layered, contextual, and subtle. These experimental rebellions did not destroy physics, they revitalized it. By forcing a confrontation with failure, they cleared the ground for new ideas that could accommodate the full richness of reality. They taught physicists to listen more carefully to what nature was saying, even when it contradicted deeply held beliefs. The enduring lesson of this second keynote is humility. Science advances not by defending its most successful theories at all costs, but by allowing them to be challenged by evidence. When experiments refuse to obey the rules, it is the rules that must change. This principle, forged in the crisis of classical physics, remains one of the most powerful drivers of scientific progress. The crisis surrounding light, heat, and radiation marked the point where classical physics did not merely struggle but openly collapsed. Until then, even serious anomalies could be treated as isolated problems. But radiation exposed a contradiction so severe that it struck at the mathematical and conceptual core of 19th century physics. The failure was not subtle, and it could not be repaired. It revealed that classical ideas about energy, continuity, and equilibrium were fundamentally incompatible with reality. Heat had long been understood as a form of motion. In classical thinking, the atoms of a hot object vibrated more vigorously than those of a cold one. This picture fit comfortably within mechanics and thermodynamics. Radiation, however, introduced a new layer of complexity. When an object is heated, it glows, emitting electromagnetic radiation across a range of wavelengths. Classical physics assumed that this radiation behaved like any other wave phenomenon. Energy was distributed smoothly and continuously across all possible frequencies. To study this process, physicists examined an idealized system known as a perfect absorber and emitter of radiation. Such a system allowed them to isolate fundamental principles without complications introduced by material imperfections. Classical theory predicted how energy should be distributed among different wavelengths at a given temperature. The logic behind these predictions was rigorous, drawing on statistical mechanics, electromagnetism, and thermodynamics, three of the most successful pillars of classical physics. The result, however, was catastrophic. According to classical calculations, as the wavelength of radiation decreased, the amount of energy emitted should increase without bound. The theory predicted that an object at any non-zero temperature would emit infinite energy in the short wavelength region. This was not a small error that could be corrected by refining assumptions. It was an outright impossibility. Infinite energy violated conservation laws, experimental observation, and common sense simultaneously. Experiments told a completely different story. When physicists measured the radiation emitted by hot objects, they found a well-defined pattern. The intensity increased with frequency up to a peak and then declined smoothly. At short wavelengths, the emitted energy dropped toward zero, not infinity. The experimental curve was finite, stable, and reproducible. No matter how carefully the measurements were repeated, nature stubbornly refused to behave as classical theory demanded. This discrepancy was so dramatic that it earned a name emphasizing its severity rather than its subtlety. It was not described as a discrepancy or an anomaly, but as a catastrophe. The term captured the sense that something fundamental had gone wrong. Classical physics, which had been extraordinarily successful elsewhere, produced predictions that were not merely inaccurate, but physically absurd. What made this breakdown especially troubling was that the derivation of the classical result was logically sound. There were no obvious mathematical mistakes. The assumptions used were consistent with the broader framework of physics at the time. Energy was assumed to be continuous. Electromagnetic waves were treated as harmonic oscillators. Thermal equilibrium was described statistically. Each piece of reasoning seemed reasonable. Yet together, they led to nonsense. This forced physicists to confront a painful realization. The problem was not in the calculations, but in the assumptions themselves. Something deeply ingrained in classical thinking did not apply to the behavior of radiation. The idea that energy could be divided into arbitrarily small amounts, spread continuously across all frequencies, appeared to be false. Radiation experiments also exposed limits in the classical understanding of temperature and equilibrium. Classical thermodynamics described heat flow and energy exchange in macroscopic systems with remarkable accuracy. But when these ideas were applied to microscopic modes of radiation, they failed. The distribution of energy among the possible modes of electromagnetic radiation did not follow classical expectations. Nature seemed to impose constraints that classical theory could not justify. Attempts to fix the problem within the existing framework quickly ran into dead ends. Various modifications were proposed, each trying to suppress the unphysical divergence at short wavelengths. These fixes were mathematically artificial and lacked physical motivation. They worked only by coincidence and failed to generalize. Worse, they often contradicted other well-established results. The theory was being bent out of shape to fit reality, and the strain was obvious. The deeper implication of this failure was profound. Classical physics assumed that systems in thermal equilibrium shared energy equally among all available modes. This principle, known as equipartition, had been enormously successful in explaining the behavior of gases and solids. Radiation experiments showed that equipartition simply did not apply to electromagnetic modes. Some modes were effectively frozen out, receiving far less energy than classical theory required. This selective distribution of energy had no place in classical reasoning. There was no mechanism to prevent energy from flowing freely into all possible modes. Yet experiments showed that such a restriction existed and was fundamental. Nature itself was enforcing limits that classical physics could not justify. The crisis of radiation was not confined to laboratory curiosities. It struck at the heart of astrophysics and cosmology. Stars emit radiation. The cosmic environment is filled with electromagnetic energy. If classical theory were correct, the universe would be unstable, radiating infinite energy at short wavelengths. The very existence of a stable universe contradicted classical predictions. Equally unsettling was the fact that radiation experiments were among the most precise in physics. They were not plagued by measurement uncertainties or uncontrolled variables. The results were clean, systematic, and robust. This left no room for doubt. The failure lay squarely with the theory. As the implications sank in, physicists realized that the breakdown was not limited to radiation alone. Heat capacity measurements in solids showed similar deviations from classical predictions. At low temperatures, materials stored far less energy than classical theory demanded. Once again, energy appeared to be restricted in ways that violated continuity and equipartition. The same pattern was emerging across different phenomena. This convergence pointed to a deeper principle at work. Energy exchange at microscopic scales did not occur smoothly. It followed rules that imposed discreteness, thresholds, and limits. Classical physics, built on the assumption of continuity, had no way to incorporate such behavior. The The failure of classical radiation theory also exposed a philosophical weakness. Classical physics had assumed that mathematical elegance and internal consistency were sufficient guarantees of truth. The radiation catastrophe shattered this belief. A theory could be logically impeccable and still be fundamentally wrong about how nature behaves. Empirical reality, not mathematical beauty, had the final authority. The crisis forced physicists to question something they had rarely questioned before: whether energy itself might be fundamentally granular rather than continuous. This idea was radical and deeply uncomfortable. It challenged centuries of intuition and contradicted the smooth flow of experience in the macroscopic world. Yet the evidence was undeniable. Something had to give. Importantly, the radiation problem did not arise at the margins of classical physics. It emerged from the application of its most central principles. This made the failure impossible to ignore. It was not a special case or a technical glitch. It was a sign that the classical framework had reached the limits of its validity. The third keynote, the crisis of light, heat, and radiation, therefore represents the moment when classical physics lost its claim to universality. The theory could no longer pretend to describe all physical phenomena. It worked brilliantly in certain domains, but it failed spectacularly in others. The dream of a single, continuous, deterministic description of nature began to dissolve. This failure was both devastating and liberating. Devastating because it invalidated deeply held assumptions. Liberating because it opened the door to new ways of thinking that could explain what classical physics could not. The catastrophe was not the end of physics, but the beginning of a transformation. As experiments continued to confirm the finite, structured nature of radiation, it became clear that a new conceptual framework was required, one that accepted limits where classical physics demanded infinities, one that allowed discreteness where continuity had been assumed, one that took experimental facts seriously, even when they defied intuition. The breakdown of classical radiation theory stands as one of the clearest examples in science of how success can conceal failure. For decades, classical physics appeared complete and unassailable. Yet in the behavior of glowing objects and emitted light, reality revealed a flaw so deep that it forced a revolution. The universe had drawn a line that classical physics could not cross. This was the moment when it became undeniable that the old rules were not enough. Light and heat were not passive extensions of classical mechanics. They obeyed principles that demanded a new understanding of energy itself. And once that door was opened, nothing in physics would ever be the same again. As the implications of the radiation crisis became impossible to ignore, physicists were forced to confront a truth that cut against the deepest habits of classical thought. The failure was not technical but conceptual. The equations had not merely overshot reality, they had revealed that the assumptions underlying them were inappropriate for the microscopic world. The catastrophe exposed a mismatch between how energy was modeled and how energy actually behaved. Nature was not continuous in the way classical physics demanded. The most unsettling aspect of the radiation problem was that it arose from principles that had been extraordinarily reliable elsewhere. Statistical mechanics had explained gases with remarkable success. Electromagnetism had unified light, electricity, and magnetism into a single, coherent theory. Thermodynamics had revealed universal laws governing heat and energy. Radiation forced these pillars into conflict with one another. When applied together, they produced an absurd result. This was not a failure at the edges of theory, it was a collision at the center. The experimental curve of radiation intensity carried a quiet but profound message. It showed that high-frequency modes did not participate freely in energy exchange. No matter how hot an object became, these modes remained suppressed. Classical physics had no reason for such restraint. If energy were continuous and equally accessible, every mode should have shared in thermal motion. Yet nature imposed a cutoff that classical reasoning could not justify. This restraint suggested that access to energy was conditional. Something prevented systems from absorbing or emitting energy in arbitrarily small amounts at high frequencies. The universe appeared to be economical, selective, and constrained in ways that contradicted the classical image of smooth abundance. Energy was not an infinitely divisible fluid, it behaved more like a currency exchanged in fixed denominations. This realization carried consequences far beyond radiation. It challenged the universality of the equipartition principle, which had been considered almost sacrosanct. If equipartition failed for electromagnetic modes, why should it hold elsewhere? The classical assumption that every degree of freedom contributes equally to thermal energy began to crumble. Nature was revealing that not all degrees of freedom are created equal. The radiation crisis also altered the meaning of temperature at a fundamental level. In classical theory, temperature was a measure of average energy distributed smoothly across motion. Radiation showed that temperature did not grant universal access to energy. Instead, it set conditions under which certain exchanges were permitted and others forbidden. Temperature became a gatekeeper rather than a simple measure. As physicists wrestled with these implications, they encountered a deeper philosophical discomfort. Classical physics had always assumed that limits were practical, not fundamental. Any restriction on energy flow was thought to arise from friction, resistance, or imperfect materials. Radiation experiments showed a limit that persisted even in idealized systems. This was not a flaw of matter or measurement, it was a rule of nature. The persistence of this limit forced a rethinking of what physical laws represent. Classical laws were often interpreted as exact descriptions of reality. The radiation catastrophe showed that laws might instead be approximations valid only within certain domains. Outside those domains, the same equations could lead not just to error but to impossibility. This was a humbling revelation. Equally transformative was the way radiation linked microscopic behavior to microscopic observables. The shape of the radiation curve depended on atomic scale processes, yet it could be measured with macroscopic instruments. This connection suggested that the microscopic world exerted a decisive influence on large-scale phenomena. Classical physics had treated these scales as conceptually continuous. Radiation revealed that the bridge between them required new principles. As the crisis deepened, it became clear that any solution would require abandoning at least one cherished assumption. Continuity was the most vulnerable. If energy exchange occurred in discrete steps rather than smooth flows, the divergence at short wavelengths could be avoided. This idea was radical precisely because it contradicted centuries of intuition. Nothing in everyday experience suggested that energy came in packets, yet radiation experiments demanded exactly that. The acceptance of discreteness did not come easily. It required physicists to separate human intuition from physical reality. The smoothness of macroscopic experience was revealed to be an emergent property, not a fundamental one. Just as a river appears continuous from afar but consists of individual molecules, energy appeared continuous at large scales while being fundamentally granular at small ones. This shift had a cascading effect on other areas of physics. Heat capacity anomalies in solids, which had puzzled scientists for years, suddenly made sense under the assumption that energy exchange was restricted. At low temperatures, many modes were inaccessible, explaining why materials stored less energy than classical theory predicted. What had once seemed like unrelated problems now appeared as manifestations of a single underlying principle. The radiation crisis also reshaped attitudes toward mathematical infinity in physics. Classical theory had tolerated infinities as formal results that might be resolved through interpretation. Radiation made this tolerance untenable. An infinite prediction for a measurable quantity was not a philosophical curiosity. It was a sign that the theory had lost contact with reality. Physics could no longer accept infinities as harmless artifacts. This realization sharpened the criteria for acceptable theories. Mathematical elegance alone was no longer sufficient. Physical plausibility, grounded in experiment, became paramount. A theory had to respect empirical constraints even if that meant sacrificing familiar concepts. The authority of nature over theory was reaffirmed in the strongest possible terms. The broader cultural impact within science was profound. Confidence gave way to caution, certainty gave way to conditionality. Physicists learned that even their most trusted frameworks could fail when pushed beyond their natural domain. This fostered a new intellectual humility and a greater willingness to entertain radical ideas, provided they were anchored in evidence. In hindsight, the radiation catastrophe appears as an inevitability rather than an accident. Classical physics had been extrapolated too far, asked to explain phenomena that lay outside its conceptual reach. Its failure was not a betrayal of its principles, but a consequence of their limits. The crisis revealed where those limits lay. Most importantly, the breakdown transformed the purpose of theory. The goal was no longer to produce a single, all-encompassing description of reality based on familiar ideas. It became to develop layered descriptions, each valid within a specific regime. Classical physics retained its power where continuity and determinism were good approximations. New principles would be required elsewhere. The third keynote thus marks a decisive turning point. The crisis of light, heat, and radiation was the moment when classical physics confronted a boundary it could not cross. The universe did not merely resist explanation, it demanded a new one. Energy was not what classical physics thought it was, and once that was acknowledged, the door to a new understanding stood open. This realization did not immediately solve the problem, but it clarified the path forward. Any successful theory would have to explain why radiation was finite, why energy exchange was restricted, and why classical predictions failed so dramatically. It would have to respect experimental facts even when they contradicted intuition. It would have to accept discreteness at the foundations of nature. The radiation crisis therefore stands as one of the most instructive moments in the history of science. It shows how deeply a theory can succeed and still fail, how mathematics can be flawless and reality unforgiving, and how progress often begins not with answers but with contradictions. Classical physics did not fall because it was weak. It fell because it was pushed to explain a universe that was deeper and stranger than it had ever imagined. When matter itself began to misbehave, the crisis in classical physics moved from abstract theory into the very substance of reality. Until this point, failures could be blamed on light, radiation, or exotic experimental conditions. Matter, however, was supposed to be solid ground. It was assumed to follow mechanical rules more faithfully than anything else. Atoms, in classical thinking, were simply very small objects obeying the same laws as planets and machines. When experiments revealed that matter did not behave mechanically at all, the classical worldview lost its last refuge. The classical picture of the atom imagined electrons orbiting a central nucleus in smooth, well-defined paths, much like planets around the sun. This model felt natural and reassuring. It extended familiar celestial mechanics down to microscopic scales. But it contained a fatal flaw. According to classical electromagnetism, any charged particle that accelerates must emit radiation. Orbiting electrons were constantly accelerating, which meant they should continuously lose energy. As they lost energy, they should spiral inward and crash into the nucleus. Calculations showed that this collapse should occur almost instantly. Atoms, according to classical physics, were catastrophically unstable. Matter itself should not exist in any persistent form, yet the universe was clearly filled with stable atoms, molecules, solids, and living beings. The very fact that you could hold an object in your hand was a direct contradiction of classical prediction. This was not a small inconsistency, it was an existential failure. Attempts to ignore or patch this problem failed. There was no classical mechanism that could stabilize atomic orbits without violating other well-established laws. The stability of matter, something so fundamental that it had never been questioned, suddenly became inexplicable. Classical physics could describe how atoms moved if they existed, but it could not explain why they existed at all. Further experimental evidence deepened the crisis. When scientists examined the light emitted by atoms, they found that atoms did not radiate energy continuously. Instead, they emitted light at very specific frequencies, producing sharp spectral lines. Each element had its own unique pattern. Classical physics predicted smooth, continuous spectra reflecting the continuous motion of electrons. The observed discreteness had no place in the classical framework. This discreteness implied that electrons were not free to occupy any arbitrary state. They were restricted to specific configurations, forbidden from existing in between. Matter, at its most basic level, appeared to follow rules of permission and prohibition rather than continuous motion. The atom behaved less like a tiny solar system and more like a structured system governed by invisible constraints. Scattering experiments made the situation even stranger. When particles were fired at atoms, the results showed that atoms were mostly empty space, with a tiny, dense nucleus at the center. This discovery overturned the idea of matter as a solid, continuous substance. Solidity, it turned out, was an illusion arising from interactions at deeper levels. Matter was not solid in the classical sense, it was structured emptiness held together by forces that classical mechanics could not fully explain. Even more unsettling was how electrons behaved in these experiments. They did not follow clear trajectories. Instead of moving like tiny bullets, they spread out, diffracted, and interfered in ways characteristic of waves. Yet when detected, they appeared as localized particles. Matter was exhibiting a dual nature that defied classical categories. It was neither particle nor wave in any conventional sense. This behavior forced physicists to confront a breakdown in the concept of trajectory itself. In classical physics, an object's path through space and time is fundamental. If you know the forces acting on it, you can calculate its exact motion. Experiments with electrons showed that such paths could not always be defined. Asking where an electron was between interactions became a meaningless question. The classical idea of motion lost its foundation. The impossibility of defining precise motion also undermined determinism. If matter did not have well-defined positions and velocities at all times, then the future could not be calculated with certainty, even in principle. This was not due to ignorance or experimental limitations. It was a feature of how matter behaved. Identical experiments produced different outcomes, governed by probabilities rather than certainties. What made this especially disturbing was that matter underpinned everything else in physics. If atoms did not behave classically, then chemistry, materials, and even biology rested on non-classical foundations. The failure was not confined to an obscure corner of theory. It extended to the building blocks of all physical reality. Classical physics had assumed that complexity arose from the interaction of simple, well-defined parts. Experiments showed the opposite. At the most basic level, matter was already strange, constrained, and probabilistic. The familiar behavior of macroscopic objects emerged from this strangeness, not from simple mechanical rules scaled up. The behavior of matter also revealed that observation could not be separated from reality. Measuring atomic systems altered their behavior in unavoidable ways. There was no way to peek at matter without influencing it. This contradicted the classical idea that properties existed independently of measurement. Matter did not passively reveal its state, it responded to being observed. By this stage, it was clear that classical physics had reached a breaking point. It could not explain why matter was stable, why atoms emitted discrete spectra, why electrons lacked definite trajectories, or why measurement played such an active role. These were not peripheral issues. They were central facts about the physical world. The fourth keynote, matter behaving in impossible ways, marks the moment when classical intuition completely lost its authority. Matter was not made of tiny machines obeying familiar laws. It followed principles that were alien to everyday experience. The solidity of objects, the stability of atoms, and the structure of matter all depended on rules that classical physics could not accommodate. This realization forced a profound shift in thinking. Matter was no longer something that could be fully understood by analogy with visible objects. It required a new conceptual language, one that accepted discreteness, probability, and the limits of classical description. The failure of classical physics was no longer theoretical. It was written into the very existence of matter itself. At this point, the question was no longer whether classical physics was incomplete. That was beyond doubt. The question became how to build a new framework capable of explaining why matter exists, why it is stable, and why it behaves the way it does. The answer would redefine physics, but the failure that made it necessary began here, with matter doing what classical physics said was impossible. The breakdown of determinism marked one of the most profound intellectual shocks in the history of physics. For centuries, determinism had been more than a scientific principle, it was a worldview. Classical physics taught that the universe operated like a perfectly constructed machine. Every event was the inevitable consequence of prior conditions. If the present state of a system were known with complete precision, the future could be calculated with absolute certainty. Uncertainty was never considered fundamental. It was merely a sign of ignorance, missing information, or imperfect measurement. This belief shaped how reality itself was understood. The past fixed the present, and the present fixed the future. There was no room for genuine chance in nature. Randomness existed only in human descriptions, not in the universe itself. From the motion of planets to the collision of particles, everything followed precise laws. Determinism gave classical physics its confidence and its philosophical power. The first cracks in this idea did not come from speculation, but from experiment. As physicists probed deeper into the behavior of atoms and radiation, they encountered outcomes that could not be predicted exactly, even in principle. Repeated experiments performed under identical conditions did not produce identical results. Instead, they produced patterns of outcomes that could only be described statistically. This was not experimental noise. It was reproducible, structured uncertainty. At first, many physicists assumed that hidden variables must be responsible. Perhaps there were unknown details in the system that, if discovered, would restore determinism. This assumption was natural. Classical physics had trained scientists to believe that uncertainty always had a cause. But as experimental techniques improved, the space for hidden explanations shrank. The randomness did not disappear. It persisted even as control over experimental conditions became extraordinarily precise. What made this randomness so disturbing was that it appeared at the most fundamental level of description. It was not the complexity of the system that caused unpredictability. Even the simplest systems, single particles, isolated atoms, displayed outcomes that could not be predicted with certainty. Physics could no longer say what would happen in a specific event. It could only assign probabilities to different possibilities. This represented a complete reversal of the classical ideal. Prediction no longer meant certainty. It meant likelihood. The laws of physics did not dictate outcomes, they constrained them. They defined what could happen and how often, not what must happen. This shift was not a matter of interpretation. It was forced by experimental fact. The collapse of determinism also undermined the classical notion of causality. In the deterministic view, causes uniquely determined effects. The same cause always produced the same effect. In the new experimental reality, the same preparation could lead to different outcomes. Cause and effect became statistical rather than absolute. Causes influenced probabilities instead of dictating results. This did not mean that physics became subjective or arbitrary. The probabilities themselves were precise and highly predictive. Large numbers of events followed strict statistical laws. What changed was the status of individual events. At the most fundamental level, nature did not commit to a single outcome until it happened. The future was no longer a fixed script waiting to be revealed. It was a range of possibilities waiting to be realized. The role of measurement became central to this breakdown. In classical physics, measurement revealed what was already there. In the new experimental regime, measurement participated in defining outcomes. Certain properties did not have definite values until they were measured. This was not due to technological limitations. It was a structural feature of how nature behaved. The act of measurement was inseparable from the phenomenon being measured. This shattered the classical image of an objective universe evolving independently of observers. Reality could no longer be described as a collection of properties with fixed values at all times. Some aspects of nature existed only as probabilities until interaction occurred. Determinism, which relied on well-defined initial conditions, lost its foundation. The psychological resistance to this idea was immense. Determinism was deeply tied to the belief that the universe was rational in a familiar, mechanical sense. Its collapse felt like a loss of order itself. Many physicists struggled to accept that chance might be fundamental rather than superficial. The idea that the universe could not predict its own future in detail was deeply unsettling. Yet the evidence was relentless. Every attempt to restore classical determinism ran into contradictions with experiment. The universe behaved as if it genuinely did not decide certain outcomes in advance. This was not philosophical pessimism. It was an empirical conclusion. Nature, at its deepest level, was not deterministic in the classical sense. Importantly, this did not mean that macroscopic determinism vanished. At large scales, where enormous numbers of particles are involved, probabilities average out. The familiar predictability of everyday life emerged from underlying uncertainty. Determinism was revealed to be an approximation, not a fundamental truth. The classical world was stable not because nature was deterministic, but because randomness canceled out at large scales. This realization transformed how physicists understood laws of nature. Laws were no longer commands dictating exact behavior. They were statistical rules governing distributions of outcomes. Physics became a science of probabilities, not certainties. This shift required abandoning centuries of intuition about cause, effect, and predictability. The breakdown of determinism also had profound philosophical implications. It challenged the idea that the universe was a closed, predetermined system. It reopened questions about time, causality, and the limits of knowledge. If the future was not fixed, then prediction had fundamental limits. There were things that could not be known in advance, not because of human weakness, but because of how reality itself was structured. The fifth keynote marks the moment when classical certainty finally collapsed. The universe was no longer a machine ticking toward a predetermined future. It was a dynamic system unfolding within constraints but not fixed in detail. Order remained, but it was a different kind of order, probabilistic, contextual, and subtle. This was not the abandonment of reason, it was its transformation. Physics did not become less rigorous, it became more honest about what could and could not be known. Determinism, once the bedrock of physical explanation, was revealed to be a powerful illusion born from limited experience. The breakdown of determinism forced science to grow up. It replaced comforting certainty with disciplined uncertainty. It taught physicists that prediction has limits and that those limits are written into the fabric of the universe. In doing so, it changed not only physics, but humanity's understanding of reality itself. As physics pushed deeper into the microscopic world, it became clear that the failure of classical physics was not confined to specific phenomena like radiation or atomic stability. The problem was far more unsettling. Reality itself, at very small scales, did not behave in ways that human common sense could tolerate. The deeper scientists looked, the more the universe violated the expectations built from everyday experience. What had once seemed like universal truths turned out to be habits of perception shaped by life in a macroscopic world. Common sense is rooted in scale. Humans evolved to navigate objects that are neither extremely small nor extremely fast. In this realm, things have definite positions, follow continuous paths, and behave predictably. Classical physics was built upon these intuitions and then elevated to universal principles. It assumed that if something was true for stones, arrows, and planets, it must also be true for atoms and electrons. Experiments shattered this assumption completely. At small scales, objects refused to stay in one place. Particles could not be pinned down to precise locations without fundamentally altering their behavior. The more carefully physicists tried to determine where something was, the less they could say about how it was moving. This was not a technological limitation. No improvement in instruments could overcome it. Nature itself enforced a trade-off that had no analog in everyday life. The idea that an object could have a precise position and velocity at the same time, a cornerstone of common sense, simply did not apply. Even the concept of an object existing at a single point in space became questionable. Experiments revealed that microscopic entities behaved as if they were spread out, occupying regions rather than points. They could pass through multiple paths simultaneously and interfere with themselves. This behavior had no counterpart in the visible world. A stone cannot go through two doors at once. An electron, under the right conditions, behaved as if it could. Time itself began to behave strangely. In classical thinking, events unfold in a clear sequence, first this, then that. At small scales, cause and effect became blurred. Certain processes could not be ordered in a simple temporal chain. The timing of events lost its absolute meaning, replaced by correlations that defied classical sequencing. Reality no longer unfolded like a story with a clear beginning, middle, and end. Perhaps the most disturbing violation of common sense was the way systems behaved as unified wholes even when separated. Classical intuition insists that objects influence each other only through direct contact or through forces acting across space. At small scales, experiments showed that parts of a system could remain linked regardless of distance. Actions performed on one part affected the behavior of another instantaneously, without any signal traveling between them in the classical sense. This did not fit into any familiar category of cause and effect. This behavior was not a trick of interpretation. It was measurable, repeatable, and precise. The universe was not composed of independent pieces interacting locally in simple ways. It was deeply interconnected at levels that classical physics could not describe. Common sense, which relies on separation and independence, was no longer a reliable guide. Energy too defied intuition. Instead of flowing smoothly, it appeared in discrete jumps. Systems could not absorb or release arbitrary amounts of energy. They changed in sudden steps, skipping intermediate values entirely. To a mind trained in continuity, this behavior seemed absurd. Nothing in everyday experience prepares us for a world where transitions happen without passing through intermediate states. Yet this was exactly what experiments revealed. The idea of identity also became unstable. In classical physics, objects are distinguishable. You can label them, track them, and tell them apart. At small scales, identical particles lost individuality. They became fundamentally indistinguishable, not just practically but in principle. Swapping two such particles made no observable difference to the system. The notion of tracking, which one is which, lost meaning. Reality no longer respected the common sense idea of individuality. Measurement further complicated the picture. In the macroscopic world, measuring something reveals its properties without changing them in essential ways. At small scales, measurement altered what was being measured. There was no way to observe a system without participating in its behavior. The observer could not be separated from the observed. This contradicted the deeply held belief that reality exists independently of observation in a fully defined state. The cumulative effect of these discoveries was profound. Common sense had always served as an informal guide to what was physically possible. Physics had refined it but never outright contradicted it. Now, common sense was actively misleading. Ideas that felt obvious, continuous motion, local causality, independent objects, were failing one by one. The microscopic world obeyed rules that felt alien, even paradoxical. This created an intellectual crisis not just for physics, but for human understanding. If reality at its most fundamental level was so strange, how could it give rise to the familiar world of everyday experience? How could a world governed by probabilities, non-local connections, and indeterminate properties produce solid objects, stable structures, and predictable behavior? The answer was not immediately clear. But the question itself marked a turning point. The realization gradually emerged that common sense is not wrong, it is limited. It works extraordinarily well within the scale for which it evolved. At larger scales, the strange behaviors of the microscopic world average out. Probabilities become certainties. Discreteness becomes smoothness. Interconnections fade into apparent independence. The classical world is not fundamental, it is emergent. This insight reshaped how physicists thought about explanation. The goal was no longer to force reality into familiar categories, but to understand how unfamiliar rules give rise to familiar appearances. The strangeness of small scales was not a flaw in theory, it was a feature of nature. Physics had to learn to describe a reality that made no intuitive sense, and then explain why that reality looked sensible from a distance. The sixth keynote represents the final collapse of classical intuition. By this point, it was no longer possible to believe that deeper understanding would restore common sense. The universe was not strange because humans misunderstood it. It was strange because strangeness was fundamental. Accepting this required a shift in intellectual attitude as much as a change in equations. This was one of the most humbling lessons science ever learned. Human intuition, refined by survival and everyday experience, was not a universal guide to truth. Nature operated according to principles that were precise but deeply counterintuitive. Understanding reality required trusting experiment and mathematics over when they led far beyond the comfort of common sense. The defiance of intuition at small scales did not weaken physics, it strengthened it. It freed science from the constraint of familiarity and allowed it to describe the universe as it is, not as humans expect it to be. The cost was the loss of comforting images. The reward was a deeper, more accurate understanding of reality, one that acknowledged that the universe, at its foundations, is far stranger than common sense could ever imagine. The collapse of classical physics did not leave a void for long. What emerged from its failure was not confusion, but a radically new way of understanding nature. The birth of this new framework was not sudden or clean. It arose from desperation, contradiction, and the recognition that the old concepts were no longer sufficient. Physics had reached a point where continuing along the classical path was impossible. To move forward, it had to reinvent its foundations. This reinvention began with a profound shift in attitude. Classical physics had sought certainty, continuity, and visualizable mechanisms. The new approach accepted uncertainty, discreteness, and abstract descriptions as fundamental features of reality. The goal was no longer to force nature into familiar images, but to let experimental facts dictate the form of theory, even when that form defied intuition. This marked a decisive break with centuries of tradition. One of the most important changes was the acceptance that energy and physical quantities were not infinitely divisible. Instead of flowing smoothly, they came in discrete units. This idea initially appeared as a mathematical trick to fix experimental problems, but it quickly revealed itself as a fundamental principle. Nature, at its deepest level, operated in steps rather than flows. What seemed continuous at large scales was built from countless tiny jumps at small scales. Alongside this came a new understanding of probability. Probability was no longer a statement about ignorance. It became a statement about reality itself. The future was not fully determined by the past in a strict sense. Physical laws no longer specified exact outcomes, but distributions of possible outcomes. This did not weaken the predictive power of physics, it redefined it. Precision shifted from individual events to statistical patterns. The role of the observer was also re-examined. Classical physics had treated observation as passive, something that revealed properties without altering them. The new framework recognized that observation was an interaction, not a neutral glance. Measuring a system was not separate from the system's behavior. This did not mean that reality depended on human consciousness, but it did mean that physical properties could not always be defined independently of how they were measured. Equally revolutionary was the abandonment of visualizability as a requirement for understanding. Classical physics relied heavily on mental pictures, trajectories, forces, waves, and collisions. The new theory accepted that some aspects of reality could not be pictured in everyday terms. Mathematics became the primary language of description, not because it was elegant, but because it was honest. It could express relationships that words and images could not. This shift was deeply unsettling. It forced physicists to let go of the idea that understanding meant being able to imagine how something worked. Instead, understanding meant being able to predict outcomes correctly and consistently, even if the underlying processes defied visualization. Reality no longer needed to make sense to human intuition to be real. The new framework also unified previously disconnected failures of classical physics. Problems involving radiation, atomic stability, spectral lines, heat capacities, and particle behavior were no longer isolated mysteries. They became interconnected consequences of a deeper structure. What classical physics could not explain separately, the new theory explained collectively. This coherence was one of its strongest validations. Another crucial development was the recognition that classical physics had not been wrong, but incomplete. It remained extraordinarily accurate within its domain. The new understanding did not overthrow classical laws, it placed them within a broader context. Classical behavior emerged naturally when large numbers of particles were involved, or when energies were high enough that discreteness became negligible. The old world was not destroyed, it was explained. This idea of emergence became central. The smooth, deterministic world of everyday experience was not fundamental. It arose from averaging over immense numbers of microscopic events. Probability became certainty at scale, discreteness became continuity, strangeness faded into familiarity. The classical world was revealed as a special case, not the foundation of reality. The philosophical implications were immense. Reality was no longer a static machine unfolding along a predetermined path. It was a dynamic process governed by constraints rather than certainties. Knowledge had limits that were not merely practical but fundamental. Some questions could not be answered because they did not correspond to anything physically meaningful. This was not a failure of science, but a clarification of its scope. The birth of the new framework also changed how physics approached truth. Instead of seeking final answers, it embraced provisional models. Theories were judged not by how comfortable they felt, but by how accurately they described nature within defined limits. This fostered a culture of humility and openness to revision. Success no longer implied finality. Importantly, this transformation did not occur because physicists wanted novelty. It occurred because nature demanded it. Every step away from classical intuition was forced by experimental fact. The new ideas were not adopted because they were philosophically appealing, but because nothing else worked. The universe left no alternative. The impact of this new way of thinking extended far beyond physics. It influenced chemistry, materials science, electronics, and eventually technology in ways that reshaped civilization. Devices that rely on microscopic behavior became possible only because physics accepted its own limits and moved beyond classical assumptions. The abstract ideas born from crisis became the foundation of the modern world. At a deeper level, this transformation changed humanity's relationship with knowledge itself. It taught that understanding does not require certainty, that prediction does not require determinism, and that reality does not owe comfort to intuition. It revealed that the universe is subtle, layered, and richer than any single framework can capture completely. The seventh keynote, the birth of a new way of understanding nature, marks the true resolution of classical physics' failure. The crisis was not resolved by repairing old ideas, but by transcending them. Physics learned to live with uncertainty, to trust experiment over intuition, and to accept abstraction as a legitimate form of understanding. This new way of thinking did not close the book on physics. It opened it wider than ever before. Each answer revealed deeper questions. Each success exposed new limits. The universe was no longer seen as a puzzle with a single solution, but as a structure with many layers, each requiring its own language, In the end, the failure of classical physics was not a tragedy. It was a turning point. It forced science to abandon the illusion of finality and embrace a more flexible, honest vision of reality. From that failure emerged a deeper understanding, one that acknowledged the strangeness of nature without trying to tame it, and in doing so, brought humanity closer to how the universe truly works.